Thank you all for coming. We're very excited to have Ilya Tolstikhin, who's going to present today his work on Wasserstein Autoencoders. It's a paper accepted in ICLR and ICLR as an oral. And a brief bio for Ilya. So he received the diploma in applied mathematics from the Lomonosov Moscow State University in 2010. And did his PhD in theoretical computer science from the Dorodnichin.
Dorodnichin, yeah.
Yes. Computing Center of the Russian Academy of Sciences, 2014. He worked there with Konstantin Vorontsov on statistical learning theory. In 2014, he moved to Germany and joined Bernard Scholkopf's group at Max Planck Institute for Intelligent Systems. And he's focusing on theoretical understanding of various learning procedures and statistical guarantees, describing the performance under different problem settings. And lately he's been very interested in unsupervised generative modeling with the goal of explaining the success of the existing methods. Yes. So, well, let's thank Ilya.
Okay. That was a great introduction. Thank you. Thank you a lot for having me here. And I'm very excited to give this talk in front of this audience. So I will be talking about Wasserstein autoencoders. And hopefully I will have some time to mention also our more recent work in that direction. And everything I'm talking here is a joint work with my colleagues, with Olivier Bousquet and Sylvain Guely from Google Brain Zurich, and Carl-Johann Simon Gabriel, Paul Rubinstein, and Bernard Scholkopf of Max Planck Institute for Intelligent Systems in Tübingen. And before we dive to the formal part of the talk, let me give you a short two-slide version of my talk so that we are on the same page. The topic of my talk are unsupervised generative models. And basically, roughly speaking, the goal is the following. You have a bunch of data points. You want to come up with a model capable of generating synthetic points looking in a way similar to your training examples. And arguably, this field is dominated currently by two major approaches. One is autoencoders, or more specifically variational autoencoders, and the others are generative adversarial nets. And here you see synthetic pictures generated by models trained on two different data sets with faces. And by the way, throughout this talk, I will be mostly talking about natural picture data sets. So I will use terms inputs, data points, pictures, and images interchangeably. So on the left-hand side, you see VAE results, and on the right-hand side, you see GAN results. And I need to say, of course, that pictures on the left-hand side were generated by me, and I'm not the best hacker in the world. And while on the right-hand side were taken from this recent paper by NVIDIA, so they come from an extremely well-tuned and well-engineered model, huge model. But I still hope that these pictures kind of capture the, the main distinctive features of these two different approaches, which I'm now going to compare, basically. So variational autoencoders, very well-established method with a solid theoretical, foundation. They come with both encoders, which can be used to featureize your real data points, or to represent the data as finite dimensional vectors in Euclidean space, which are also called codes or latent codes, and decoders, which can be used to sample from these models. VAs have extremely stable training, and they often lead to a very nice, smooth, latent manifold structure. Unfortunately, it happens that they often tend to produce samples which look kind of blurry. Meanwhile, GANs happen to be capable of, so I will have to be pushing all the time. Let me quickly turn off the sleep mode. Okay, never. Okay, now should be fine, huh? My talk will last forever, so we need never. Okay, so they are capable of generating samples of extremely high visual quality and sharpness. Unfortunately, this comes at a price. First, their training corresponds to a min-max problem, which is known to be numerically unstable. They come only with generator, which can be used only to sample the synthetic data points. And if you are interested in representations and features, unfortunately, there is no default way of featureizing examples with trained GAN models. So basically, to summarize, I think generative adversarial nets are extremely useful, and these are very powerful techniques applicable in various cases, but they come with a major downside, which is partially explained by the following. If you take the state-of-the-art GAN architecture and you run 10 models with the same architecture, same hyperparameters, but different random seeds, you may end up with 10 models of extremely different quality, okay? And this is something confirmed in a recent paper called, I think, Are All GANs Created Equal? From people from Google Brain Zurich, where they showed exactly that. So this means that if you want your generative model to be reliable, stable, and consistently produce samples of good visual quality, then perhaps GANs are not the best choice. Moreover, if you're interested in features, in representation learning, also GANs perhaps are not the best choice. And in my personal opinion, autoencoder architectures may be better suited for these needs. And here I turn to the outline of my talk. So basically our goal was to develop better generative autoencoding architectures. And as a result, we introduced this new framework which we called Wasserstein autoencoders. They share most of nice features of variational autoencoders. They have stable training. They lead to nice test reconstructions. They lead to nice latent space manifold. And they are theoretically well-grounded, while having samples of slightly improved quality and also being a bit more flexible in design choices. So that's it. That's the whole kind of sketch of my talk. And now to the contents. I will first take you through a short introduction to variational autoencoders and GANs. I'm sure you're all experts and you know about these things, but I just want to motivate the derivations of Wasserstein autoencoders. Then I'll introduce you to this optimal transport distance and state the main theoretical results of our work, which then naturally leads to a learning algorithm which we call Wasserstein autoencoders. I will show you two particular implementations, WA GAN and WA MMD, and then I'll show you some preliminary experiments on MNIST and Celebi datasets. Finally, I will discuss some related literature, and if time permits, I would also like to mention you some of our recent results with Paul Rubinstein from our lab, where we are trying to answer some of the questions related to the design choice in WAs, mostly related to the latent space. And in particular, we demonstrate that WAs managed to outperform the state-of-the-art method called beta VAE on a recently introduced disentanglement benchmark dataset, where WAs somehow simultaneously achieve better reconstruction quality and disentanglement quality. Okay? So that's the outline. And now let me dive into the formal part of the talk, and I will start with formally introducing the problem. So imagine we have an unknown data distribution Px, and we observe endpoints sampled independently from this distribution. Our goal is to find a model distribution Pg, which is in a way similar to the data distribution. And for now, I'm not specifying what does it mean to be similar. Throughout this talk, I will be discussing only latent variable models, which are probabilistic models described by two steps. First, you sample a latent code, Z, from a prior distribution defined over the latent space. Typically, latent space is going to be a Euclidean space of 100 to 200 dimensions, and PZ could be Gaussian or uniform on the box, things like that. Then you take this code in the latent space, and you want to transform it to the image in the pixel space, okay, with a perhaps random transformation. And in this talk, I will say deterministic transform when I mean a function, deterministically mapping a point in the latent space to the point in the picture space. And I will say random transform when I mean a mapping which takes a latent code and maps it to the distribution over the image space. This will be called random transforms. So this transform is commonly known as decoder or generator, depending in which community you are, in generative adversarial nets or variational autoencoders. If all the densities are nicely defined, then your latent variable model is specified by this density, which is basically integrating the conditional distribution with respect to the prior. And an interesting thing to notice about these models is that most likely they come without analytically tractable form, because this integral most likely is not analytically tractable. However, they are very easy to sample from, because you can easily sample from your prior PZ and then map it to the image. Okay? So these models are currently known as implicit probabilistic models, and they happen to play an important role in recent advances. Okay, now all these different methods and approaches to the generative modeling basically differs in a way they define the similarity between probability distributions. And this will be the main topic of this talk. So let me turn first to GANs. Oh, sorry. So one way to look at GANs is to say that they are trying to minimize the F divergence between the true data distribution and your model, where F divergence is a rich class of distances defined on probability distributions introduced in the following way. And depending on choice of this F function, you get all the different types of divergences. You can get KL divergence, reverse KL, Hellinger, total variation, Jensen-Shannon entropy, and many other divergences popular in statistics and probability theory. Now, if you want to minimize this quantity with respect to parameters of your model, you're in trouble, because you need to know the ratio of densities, and as we know, we don't know the data distribution, and we don't have a tractable form of density of our model. So how are we going to even approach this task, right? And fortunately, it happens that there is this elegant mathematical formulation known as variational representation of F divergences. It says that the same thing can be computed as an optimization problem, where you optimize basically over all the functions the difference of expected values. Okay? And suddenly, you don't need to know the ratio of densities anymore. All you need to know is difference of expected values. And expected values is something which is easy to estimate with a sample average, right? Once you have samples. And as I said, it is easy to sample from your model, and you have a sample from the data distribution. So GANs proceed in this way. They take latent variable models with deterministic decoder transformations. They estimate those expected values with sample averages. They parameterize all the involved functions with deep nets, and finally optimize this objective in alternating SGD steps. When this framework is specified for a particular choice of F function corresponding to the Jensen-Shannon divergence, it leads to perhaps the most standard version of vanilla GAN, where this function T starts playing a role of a classifier or discriminator, trying to separate between real data points and synthetic generated data points. Okay? Now, these GANs happen to generate samples of high visual quality, or in other words, they have a high precision. And this is evident from the objective of generator. Basically, no matter what generator produces, it should look reasonable to the trained discriminator. Okay? This explains why sample looks so good. On top of that, this adversarial training happens to be an extremely powerful and nice tool applicable in various settings. It can be used for estimation of ratio of densities in high dimensions and stuff like that, so it is extremely useful. Unfortunately, all of this comes with a price, which is basically numerically unstable min-max training. And also, as I already said, you can only sample from the trained GAN models. There is no encoder by default. Finally, maybe this is a bit lame argument, but theoreticians may find minimizing the lower bound to be a bit suspicious, because if you want to minimize quantity, you should better minimize an upper bound on it and not a lower bound. And minimizing a lower bound is exactly what seems to be happening in GANs. Okay? And on top of that, there seems to be no incentive for generator to cover all the modes of the data. Because if you stare at this objective, you see that all the generator needs to do is to fool the discriminator, right? So this is often linked to this mode collapse problem when GAN produces several pictures and not covering all the modes. On the other hand, we have variational autoencoders, very well, theoretically grounded methods, which commit to minimizing KL divergence between the true data distribution and the model distribution, which is, of course, equivalent to maximizing marginal log likelihood or minimizing negative marginal log likelihood. They proceed with developing an upper bound on this quantity of interest, which is based on special properties of KL divergence. The bound, which is usually known as the variational lower bound. In this case, I am reusing it as an upper bound, but it is the same thing. It says if you take any conditional distribution Q, which is often known as encoder, this is a random transformation from images to the latent codes, then this upper bound holds. Okay? So now the objective of VAE comes with two terms. The first term, often referred to as a reconstruction term, it makes the encoder-decoder pair to nicely reconstruct the training images, while the second term can be seen as a regularizer. If we drop this term, we end up with unregularized autoencoders. They are known to be able to reconstruct very nicely all the training images, but they lead to a nasty structure in the latent space, where all the input images end up being mapped to non-intersecting tiny balls chaotically scattered across the latent space, and it becomes impossible to sample from this structure. Okay. This regularizer makes those tiny balls to be more grouped in the center to match the prior, and this leads to this nice latent manifold structure. So then variational autoencoders can be used with any decoder distributions as long as the log density can be evaluated and differentiated with respect to its parameters. They often come with Gaussian prior and Gaussian encoders to make this KL term tractable. Finally, all the functions are parameterized with deep nets, and one would apply stochastic gradient descent on this upper bound. Now, VAEs happen to have a very high recall, meaning they manage to cover all the data modes. And again, this can be seen from the objective. So the decoder, this function G, should be able of reconstructing all the training points. And for that, it should be able to generate all the training points, right? So it means you get the coverage. They correspond to a nice numerically stable mean-mean training. They come with encoders and decoders, so you can featureize and sample. And now we are maximizing the lower bound, or in other words, we are minimizing the upper bound, right? And minimizing an upper bound is something you want to do, okay, compared to minimizing lower bound. However, the high recall comes at the price of lower precision. Basically, VAE spend a lot of power on modeling all the different modes of data. And there is no power left for modeling details of every individual modes. That's kind of their problem. In our work, we propose to shift the focus from F divergences, which is the case both for GANs and VAEs, at least in the way I introduced them, to another family of divergences known as optimal transport distance. And the optimal transport, and more specifically the Wasserstein distance, was kind of observed recently to be particularly well suited for generative modeling field in the GAN literature. The optimal transport is yet another way to define a family of divergences or similarities between two probability distributions. And the main idea is to take the cost function or a distance defined between 2 points in the space and leverage it to the level of distributions over the same input space. And one of the famous Kantorovich formulations of the optimal transport defines it as the minimal expected cost between two input points jointly distributed according to this gamma distribution, which is also known as a coupling. Okay? And the gamma is constrained to have very particular marginals. The reason for this name coupling can be seen if you factorize this joint distribution as a product of marginal times conditional. Okay? You can do it in two ways, right? With respect to first coordinate or the second. And you see that in this constrained optimization problem, the marginals are fixed, right? So all we are looking through here, we are only tuning the conditional component of this joint. And the conditional distribution may be seen as a way to link values of two random variables. That's the coupling. In particular case, if you choose this cost C to be a distance, you get the P-Wasserstein distance. And this is the reason we called the method Wasserstein autoencoders. But it applies more generally to any cost function C. And kind of the main theoretical result of our work was to show that when specified to latent variable models, when this PG is a latent variable model, this expression can be equivalently rewritten where the constraint optimization with respect to joint distribution is now replaced with a constraint optimization with respect to probabilistic encoders, which are constrained in a very specific way. We ask the marginal distribution of encoded real images to match the prior. The other name for this marginal is the aggregated posterior. What we are doing is we are sampling pictures from the true data distribution. We are encoding them and then averaging those green balls which we get. And we want this average to match our prior. Okay? This is the constraint. And once you have this theorem, it's quite natural to derive a learning algorithm from it, which we call Wasserstein autoencoders. Of course, if you want to minimize this form, it's still a very hard constraint variational optimization problem. And this constraint is very hard to satisfy. So what we propose to do is we propose to relax this constraint by penalizing the divergence between 2D distributions. So we take the objective, we drop the constraint, but we add the penalty, where this decalligraphic is any divergence between two probability distributions, hopefully non-negative, and 0 if these two distributions coincide. Okay? Then lambda is any non-negative regularizer, hyperparameter of this approach. Then we basically, again, parameterize all the functions involved with deep nets, and we propose to attack it with stochastic gradient descent. And that's a min-min problem. So at this point, let me compare this formulation to variational autoencoders so that we get a better intuition of what is happening. Here you see objectives of VAE and WAE, and they look very similar. They both come with two terms, first term being reconstruction and the second term being regularizer. If you take VAEs with Gaussian decoders and Wasserstein autoencoders with a squared pixel loss, then these first terms will simply coincide. They will be the same. So the difference is hidden in the regularizers. Okay? So the regularizer of VAEs asks every individual encoded distribution to match the prior. So in other words, if we are taking our input images and encoding them, and this is a random transformation because encoders are random, we are getting those red balls. So every input image is encoded into one of these red balls. VAE asks every single red ball to match the prior. And also implicitly, this leads to these red balls intersecting. And if they intersect, this is a problem for decoder, because if point lands to the intersection of red balls, decoder doesn't know which of the input points generated this one. And this may be used to partially explain the blurriness effect of VAs. What WAE does is instead of asking every red ball to match the prior, it asks their average to match the prior. Okay, so this green ball here denotes the mixture of these red balls. And now we are asking these green balls to match the prior distribution. And this does not necessarily lead to red balls intersecting, because these red balls can arrange in certain ways so that their sum looks like what we want. Okay? And this was kind of the main intuition behind the derivations. Other differences are the following. So WAEs can be used with any encoders and decoders. You can use deterministic encoders, deterministic decoders, non-Gaussian decoders and encoders, basically whatever you want, as long as you can do the reparameterization trick, of course. Also, it can be used with any prior distributions. You want a uniform on box, use a uniform on box. Basically, whatever prior distribution allows you to estimate this penalty, you're fine. And finally, this point is a bit interesting. So WAEs are readily applicable with any pixel cost function C. You can use whatever fancy cost you develop. Theoretically, VAEs are also capable of that. But the thing is, this log density is a normalized function. If you exponentiate it and integrate, it should get to 1, right? So if you want to use VAEs with some fancy cost functions, it may require estimation of the normalizing coefficient or a partition function, which may depend on the latent code Z, and this may lead to some difficulties. And now let's look closer into the difference between regularizers. So imagine you are using Wasserstein autoencoders with KL divergence to penalize the difference between QZ and PZ. Okay? Then you have those two regularizers. On the left-hand side, the VA regularizer, and the KL here is for the WA regularizer. And they look very similar. Kind of the only difference is how the expectation with respect to the data distribution enters, right? Because here, expectation appears outside of the KL. And here, the only difference is that we took it and we put it inside of the KL. So this difference, it happens that it may be very well explained theoretically, which was done in this paper called elbow surgery. So it happens that the VA regularizer minus WA regularizer is just the mutual information of real inputs and their encodings. Okay, this can be checked. This is several lines of massaging. So it means that VAs implicitly are also trying to minimize this mutual information term. And what does it mean? It means that they are trying to make implicitly the encodings independent from the original images. This is part of the regularizer. And Wasserstein autoencoders, they just drop this term. And then it happens that there is this beautiful link to the optimal transport, which was kind of surprising to us. So this term may be partially, may partially explain this intersection of red balls, which I mentioned in the previous slide. So now all is left to do is to define what penalty are we going to use to penalize the divergence between PZ and QZ in Wasserstein autoencoders. And we propose two versions. First, you can choose this penalty to be the Jensen-Shannon divergence. Okay? Jensen-Shannon divergence is something hard to estimate, but there is an adversarial training trick on rescue. So we introduce a discriminator or a classifier in the latent space, trying to separate between samples from the prior distribution PZ and the encodings of the real data points. Okay? This is the way we are going to do it. And of course, this leads to the min-max. So there is an adversary now into the picture. And this comes with all the downsides of min-max training. However, compared to typical applications of GANs, where discriminator acts in the pixel space, which is hugely high dimensional, here, discriminator acts in the latent space, which is often low dimensional. And moreover, in this case, one of two distributions we are comparing, it is analytically known to us. It can be a Gaussian or a uniform, and it is unimodal. So it seems like a bit easier problem than a typical application of GAN. However, we also propose a non-adversarial penalty based on the maximal mean discrepancy. So details are not so important, but basically if you take a reproducing kernel, positive definite kernel K, defined on the latent space, it gives rise to this RKHS, reproducing kernel Hilbert space. And you can use this functional analytic notion to define a distance called maximum mean discrepancy, which is a divergence between the two probability distributions. Details are not so important, but it happens that if your kernel is characteristic, and many of the common kernels are known to be characteristic, for instance, Gaussian, inverse multiquadratics, Laplace kernels are all characteristic. So if the kernel is characteristic, this gives you a distance on probability distributions with all the axioms like triangle inequality and so on and so forth. And fortunately, there is a U-statistic estimator of this distance, which can be nicely combined with stochastic gradient descent. So using this U-statistic in the original objective of WAE, we can proceed with SGD. Okay. So now I'm going to show you some of the experiments we did. So first, let's start with this easier dataset MNIST, which you are all familiar with. So here, by the way, all the code is available online on GitHub here, if you're interested. Here I have results of training 3 different models. One of them is VAE, another is WAE GAN, which is the one with adversarial penalty, and the third one is WAE MMD, in no particular order. let's find out which one is better. So who of you thinks that the left samples, these are samples of the trained model. So who of you think that the left ones look the best? The middle ones? And the right ones? Oh, we have like a very uniform split into 3 sets of people, which is cool. And that was exactly my point. So by the way, the left one was VAE, then MMD, then GAN. So I wanted to make this point that, I see a major flaw in this field of generative adversarial, of unsupervised generative modeling. There is no way to compare different models. If you are training several models minimizing KL divergence, like several VAEs, in principle, you have a way, because you can compute, the elbow and compare these values, and it will tell you something about how your models are behaving. But if you want to compare a VAE model with a GAN model, what do you do? You're in trouble. And so far, there are no well-established universal ways to do so. And I think this problem should be solved before we make any conclusions on which models are better and which are not. Okay. So yeah, in this case, well, it seems that they are doing on par. You cannot say that one is worse, the others are better. Here is just to show you several of other behaviors of these the same 3 tuned models. By the way, in all the experiments, we did exactly the same amount of hyperparameter search, and we always use the same architectures for all the 3 models. Okay, to be fair. So these are test interpolations, meaning this is a test point, and this is the test point, and then I travel linearly the latent space, and I show you the decoded versions. And these are test reconstructions. So the odd rows being the true test point, and the even rows being the reconstruction. So, and it kind of looks that they are all doing reasonably well. Maybe one thing to notice is that the latent space of the WAE GAN is less smooth, and we see some weird jumps, sudden jumps. Now let's turn to a more challenging task, which is Celebi. So this is a data set of approximately 240,000 64 by 64 by 3 images containing faces. And again, we are going to tune 3 models. We spend the same amount of time on hyperparameter tuning, the same architectures, okay? And we report the best models. I will shortly tell you what the best are. So let's repeat the vote. Who thinks that the leftmost samples look the best? The middle? And the right-hand side? Oh, this is... Okay, so here is a truth. And here, we really wanted to be objective, and we wanted to use some objective way of measuring the quality. Because, what happens in this recent GAN field is people cherry-picking, people visually inspecting the samples and saying, oh, my cats look better than your cats, or no, but this one has 4 legs and this like something like that. We wanted to avoid this, basically. And we want to kind of say that we found this recently introduced FiZscore very useful for that. So FID is for Frichet inception divergence, I guess. So FiZscore takes 2 sets of points, and its goal is to compare them, and it does so by looking at activations of the huge trained inception network, and by looking at first 2 modes of statistics based on those activations, okay? And me, my colleagues, and many people found this FiZscore to be very well aligned with visual quality of images. Yes?
So you don't have an actual GAN on the input space here as a comparison, right?
We don't have, yeah. No, here are only autoencoder models.
That would look even much better.
Yes, so I mentioned this in the last line. I will tell exactly the values of FID. So basically, the smaller the FID, the better. If you take the real Celebi samples and measure their FID, you get value 2. Okay, so this is like, you cannot do better than that. If you sample uniformly from Celebi, you get 2. Now, VAE, so we were doing all this hyperparameter search, and we were choosing the models attaining best FID of samples. So we found a VAE with 63, then WAE MMD is 55, and then 42 for WAE GAN. We also wanted to measure this, sharpness of image, whatever it means, and we tried to do so with Laplace filters. So what we were doing is, you take a picture, you convolve it with this 3 by 3 Laplace filter, which is a matrix of this form, and then you compute the variance of activations. So this filter is meant to detect the edges. So if your picture is very smooth and has no edges, then all the activations will be tiny and you get a tiny variance. Now, if you have a lot of sharp edges, you should get higher variance. So this was kind of an attempt. And we got 3 times 10 minus 3 for VAEs and double of that for WAEs. And by the way, this sharpness was not taken into account when we were selecting the models. And just for reference, the sharpness of original Celebi pictures is 10 times that. So we are still quite off. So here, I want to say that we are not claiming that the problem is solved and WAE is an ultimate solution. There is still a long way to go. But we just wanted to share this, picture showing that there is some, potential in this WAE, especially with all the flexibility in design, which I will mention later. I think there is a hope to bridge this gap. And the gap is still quite large because the best GAN models, they achieve FID of 30, which is still a... So improving FID by 5 takes a lot of time. It was very hard. So it's still a huge gap. Here are some other pictures. So basically, yeah, some test interpolations and test reconstructions. And one another thing which I wanted to emphasize is the following. So I didn't see people reporting FID scores for test reconstructions when they develop autoencoding architectures. And I think these numbers are important because if you are developing an autoencoder, you have no reason to expect better samples than the test reconstructions, right? Because test reconstruction is kind of the best your model can do. And the best hope is that the samples will match quality of the test reconstructions. So here we are also reporting FID scores for test reconstructions, and they are again ordered in the same way. So 42 for VAE, 40, not such a huge gap, right, for the test reconstruction. But the WA GAN somehow attains better test reconstruction. And here, just to show you, I don't know if you see this, but it's again the test interpolation at a finer grid. So I just wanted to show you that, WA GAN manages to get the high frequency details like shape of hair, which is something especially hard for VAE, where this blurriness really comes into the picture, right? So you see some individual hair details here, I think, but maybe this is cherry picking. Now let me spend some time discussing the related work. So first, VAEs. So they minimize KL divergence. They come with mostly Gaussian prior, Gaussian decoder, and non-deterministic decoder. Wasserstein autoencoders are solving the different problem. They are trying to minimize the optimal transport. And they come with whatever prior encoder and decoder you want. There was this paper, Adversarial Variational Base, which was an attempt to allow any non-Gaussian encoders for VAEs by using adversarial trick to estimate this KL regularizer. Okay? But they're still minimizing KL divergence, and in this way they are different from minimizing optimal transport. Now, if you use WA GAN with a squared pixel difference cost, you get exactly the adversarial autoencoders, which were methods introduced earlier. So, however, so first, this is apparently kind of a first theoretical justification showing what exactly is AE trying to do. And second, WAE allow for any other cost than squared pixel difference and any other penalty, including non-adversarial penalties. And our ultimate goal is to make WAE work nicely with non-adversarial penalty. We want to get rid of the adversarial components at all. Okay. Then there was this method called InfoVAE, which independently proposed an objective very similar to WAE. However, so the reconstruction cost was similarly to VAE, was implicitly defined through the log density, and in this sense, it is kind of hard to use whatever fancy reconstruction costs you want with this model. And finally, Wasserstein GAN, which is a beast from the GAN world. So they minimize the one Wasserstein distance, through its dual formulation. In this case, there is a Kontorovich-Rubinstein duality, which gives a nice dual representation. So these methods, unfortunately, can deal only with one Wasserstein distance. And we can deal with whatever optimal transport cost we want for whatever cost function C. And we come, the Wasserstein autoencoders are autoencoding architectures, while W GANs are GANs. They can only sample. And finally, I have several minutes to mention a very recent work. So this paper is now on arXiv together with Paul Rubinstein from our lab. So here we tried to answer some of the, yes, 5 minutes, I know. Some of the questions related to the design choices you can make in WAE, mostly related to the latent space. First observation we made is, if there is a mismatch between dimensionality of your bottleneck and the intrinsic dimensionality of your data, you may end up with problems, especially if you're using WAE GAN with deterministic encoders. Let me give you an example. Imagine you have a one-dimensional data set, meaning your data set may be multidimensional, but intrinsic dimensionality is 1. Intrinsic dimensionality is roughly number of parameters you need to smoothly parameterize your data. And imagine you're doing WAE with deterministic encoders and two-dimensional latent space. So now the encoder takes the inputs and maps them to the latent space. And it's clear that the image under encoder is still one-dimensional. You're transforming your one-dimensional manifold with a smooth function, so you get a one-dimensional manifold, embed it in two-dimensional space. Okay? So this QZ distribution, the aggregate posterior, its support is one-dimensional. And WAEs, they force this QZ to match your prior, which could be uniform on a box, let's say. This problem is as hard as filling the plane with a one-dimensional curve. Okay? So there may be a problem. So we tried to see what type of nasty behavior do you get in these cases, and we did this synthetic experiment. We introduced a data set which we call fading squares. These are 32 by 32 pixel images of centered squares, gray squares on the black background. And the color of this square changes from black to the white. And it's kind of clear that it's a one-dimensional data set, right? Because every picture can be identified by one number, which is the color of the square. And here you see the result. So we used Wasserstein autoencoders with a uniform box prior. So the prior is a uniform distribution on a box. And keep in mind that when optimizing for WAE, you are doing SGD, most likely with mini batches of size, let's say 100. So every time you evaluate your penalty to match PZ and QZ, it is based only on 100 points sampled from two distributions, okay? So now what you have here, you have 100 red points and 100 blue points. Blue points being samples from the prior, and red points being samples from the QZ, aggregated posterior. Okay, to us it's kind of clear that these two distributions are not matching, right? We already see some lines. But the MMD penalty, which we used in this case, was totally fooled, and it thought that those two distributions match. Now, if we enlarge the number of points to 1,000, we clearly see that the image of encoder is this one-dimensional curve which tries to fill this square in a way I mentioned in the previous slide. As a result, decoder manages to do something, but you see that the manifold is wrong. Okay? If you start, here what you have are decoded codes corresponding to this middle picture. And if you walk along this red line, you will see that indeed it goes from a white square, gradually to a black square. But this manifold structure is meaningless. It was just a pure coincidence that it curved it in this way, right? And if you allow for random encoders, they manage to fill the missing dimensions with noise, and this makes decoder learn to ignore some of the dimensions. Okay? Here, this black line is a mean value of encoder, and then encoder just adds the noise orthogonally. You match the prior, and decoder acts in a nicer way, right? It simply ignores this vertical direction. And shortly, let me mention this part of the same work. We were playing with random encoders, and we noticed that WAEs with random encoders are doing very good on the disentanglement benchmark dataset called DisPrice. There was a paper by DeepMind introducing a method called beta VAE. Disentangled representation means that you want to learn a representation where, while changing coordinates in the latent space, this leads to semantically meaningful transforms of your data, okay? And they introduced a particular way to measure the disentanglement metric, okay? And here on this plot, vertical is a disentanglement metric, horizontal is reconstruction error, and you see a bunch of points. Every point corresponds to a trained model, and green models are beta VAE models reported in their paper, and blue and red ones are WAs. So basically, the more left and up you are, the better, because you get more disentanglement with higher precision reconstruction. And you kind of see that, you know, these points are better. And this, by the way, this disprice dataset is a dataset of black and white pictures. These are various shapes, 3 shapes, I think, hertz, rectangles, and ovals of various scale, rotation, shifts, vertical and horizontal on a black background. So the first row here are samples from disprice. What I'm showing here is reconstructions of the WAE MMD and the beta VAE, corresponding to the best achieved, not actually to the best, but among the best disentanglement scores. So this last row is a beta VAE model which achieved a good disentanglement, and we see that reconstruction kind of, they get the position of the point, but not the shape. Okay, they decode everything to these ovals, to the circles. Meanwhile, this WAE MMD model, trained in the same way, with the same disentanglement score, achieves visually much better reconstruction. So this looked very promising to us, and we think that there is potential in these WAEs. You can model, you can choose specific PZ prior to perhaps tackle tasks like that, and we are very excited. And maybe I skip this section. Basically, yeah, I mentioned that you can use whatever cost functions you want. So we are now looking into smarter cost functions. How do you develop cost function which will give you, better reconstruction? If you want to reconstruct, let's say, a picture which is very high frequency, like you have some lines on your picture. If you shift those lines by 1 pixel, L2 loss suddenly goes, maxes out. Meanwhile, if you just shift a line by 1 pixel, you still want to say that it's a reasonable reconstruction, right? So how do you develop cost functions capturing this type of stuff? Because then they can be combined with WAE to train a generative model. And yeah, that was the whole talk, 45 minutes. Any questions?
Thank you for your excellent talk. Are there any questions?
Yeah. One really pressing question, which is, you said it mathematically shown that you can take a GAN and move it to the WAE as an equivalence. It's basically a dual formulation.
For GAN?
Well, okay, no, so the primal problem is
optimal transport.
An optimal transport, but that's, if you, right. So
yeah.
you can optimize that using basically a saddle point optimization. Right?
There is no saddle point yet at this point, right? Because we replace inf with again inf, and that's the beauty. Because GANs, they go to dual.
But the one Wasserstein GAN.
Yeah, exactly. Of course. Yeah, the adversarial penalty version still uses the
so
GAN
that
trick.
gives you very pretty pictures, right?
Yes, exactly.
Okay.
Yeah.
So you show that that's equivalent to the WAE for certain choices of C, etc.
For certain choice of this penalty with which we relax, yes, okay. Constraint. Mm-hmm.
But so that's equivalent mathematically, yet there's a big gap between the quality of the, right? And you start explaining that the gap has something to do with, this objective that the VAE is different from the WAE, but it doesn't explain the big gap still that in the dual, formulation of the problem, you don't get actually very good results. So what, in your opinion, is actually causing the deterioration?
That's an excellent question. Actually, this Paul Rubinstein's work, which I mentioned in the end, was kind of trying to look into that. And the main challenge here is, unless you manage to match PZ and QZ, things can get arbitrarily bad. You can get a very nice test reconstruction, but your samples will look nothing like your test reconstruction, unless QZ equals PZ. And QZ versus PZ is still a question of matching the two distributions. They are now, of course, not in a 1000-dimensional pixel space. They are in 100-dimensional latent space. But it turned out to be still very hard to match a distribution to a 100-dimensional standard Gaussian in a 100-dimensional space. And our conjecture is that GANs are doing really good job and managing to match two distributions. So when GAN succeed, because some of the runs of GAN, they just diverge somehow, but when they succeed, they do a real good job in telling the differences between two high-dimensional distributions. And MMD is not that powerful still. So I think this is the main reason for the gap between WAE MMD samples and WAE GAN samples. We have a bit more on that in this Paul's paper, which is a bit longish to explain, but we think that there is still this problem of matching QZ with PZ. And especially, so in VAE world, you're matching one encoded distribution to QZ, to PZ, right? And in WAE, we are trying to match an average of many encoded distributions, which is kind of, in a way, even harder. It's more flexible, so there are many pros in doing so. But it's very hard, given two distributions. Given you don't have distribution, you have samples from two distributions. How many samples do you need to perform a density estimation in 100-dimensional space? Well, it's impossible to do, right? So somehow GANs are very, very good at matching those distributions. So right now, all our power we spend on trying to develop non-adversarial cost, which will be as good, at least in 100 dimensions, because then we could, yeah. Okay, yes?
I find your observation that the PL divergence for VAE and WAE differs in the mutual information really interesting.
It's not my discovery, but yeah, it is indeed very interesting.
Does this mean you think that a VAE might generalize better in the end when it comes to reconstruction loss, because there's sort of a generalization penalty in a sense?
That's a good question. So first, then I would show this picture and challenge you, because this is test reconstruction. And the FiZscore of test reconstruction with WAE is much better than for VAE. I'm not saying that one is much better, the other is worse. I'm just giving you facts. So this seems to be in contradiction with the conjecture you made right now.
Can I ask you a second question? So
yes.
Did you optimize so with a sort of comparison between two data points, or is it just independent?
Can you repeat what?
So is FID, is that a metric that compares the data points? Or?
No, so FID is a way to compare two sets of data points. Right. So you have two sets, like two bags of points, and you want to ask how similar are those two bags. Basically, that is what FID is trying to do.
And then as a follow-up, did you optimize the WAE GAN on the FID score?
No.
Okay.
We trained multiple WAE runs and selected the ones which achieved the best FID, but they were not trained to improve FID. We only used FID to later, assess the quality of the models.
Okay. Any last hyperparameter optimization in a sense, right?
A lot of hyperparameter tuning involved, yes.
Right.
Any last question?
So your approximation for the prime involves basically you're choosing a family of functions for the encoder. Your Q is coming from a family of distribution
yes.
functions from basically neural network class.
Yeah.
Do you think that this plays a role in perhaps some of the averaging effects that we see?
Of course. So the point is, so theoretically, we need to solve this constraint optimization problem. Okay, and the set of encoder distributions attaining this equation can be huge. It's non-parametric for sure, and it's huge, And we are replacing this inf with inf over smaller set, because deep nets are not capable of representing whatever distributions you want. So already at that level, there is a gap. I mean, needless to say, we are dropping the constrained optimization problem, and we are instead doing some weirdly looking penalized unconstrained problem. So kind of at this point, we lose rigorous link to the theory. But I do think that the flexibility of encoders matter, even at that level, But otherwise, I would just try various different architectures to see which one does better.
All right, our time is up. So let's thank Ilya again.
Thank you.